Yeah, hello, everybody. Nice to meet you. Thank you for the invitation. The subject of today's lecture is about the plasmons, and I will try to persuade you that the plasmons can save the world, at least the terahertz world. What you see on the slide is some formal information. I am from Centera, Center for Terahertz Research Applications. This center, this laboratory is created as a result of two successive international research agenda projects that are called Centera and Centera 2. They started at 2018 and will go 2028. And this is a common action between Institute of High Pressure Physics, Polish Academy of Sciences, and CESAMAT, one of the departments of the Warsaw Technical University. This is, of course, funds coming from Europe. They go from Europe through the Polish Science Foundation. So these are the formal information about where does it come from, where I am working now. But you will, I will start my presentation with my short CV, telling you who I am and why I dare to talk about the terahertz. And this is summarized more or less on this study. The picture that you see on it, the photo, is the picture of Professor Michel Diakonov, who is inventor and brought basic concepts about the plasma wave terahertz electronics and plasma waves in electronics. And he was my guide since 30 years. He's my guide for 30 years in looking for basic idea in physics that can bring for new developments in physics and in applications. And this plasma stuff is that is called plasma wave electronics, concerns small objects that are field effect transistors, and you see the field effect transistors on your right. That is your source, drain. This is just like a resistor, but a special resistor with a gate. And the gate changes the carrier density. And what he was dreaming about is about the plasma waves in such a box with electrons, box with the gate where you can change the density of the electrons. My CV you see on the horizontal axis down there. I finished my PhD at University of Warsaw. When I went for the sabbatical to Grenoble, Toulouse, and Montpellier. And Montpellier, finally, I got a permanent position, and I stayed there for more than 30 years as a researcher in the French Academy of Sciences, that is called CNRS, Centre National de Recherche Scientifique. And while being there, I spent 2 years in USA on a sabbatical, and then more than 1 year in Japan. And while working at University of Montpellier already at beginning 2000, I started to organize and to motivate people at the Polish Academy of Science, at UniPress, Institute of High Pressure Physics, to start terahertz activity. Although terahertz activity in Warsaw started mainly through the Professor Greenberg lab at Warsaw University, this activity in terahertz appeared to be relatively dynamic, and support from Polish Academy of Science allowed us to create a rapidly working laboratory. So you know where I am from and where is the subject from. Let's go directly to subject or the plan of seminar or lecture. I will. My purpose is to tell you if and how it is written here, plasmonic nanostructures can be operated as terahertz voltage tunable or voltage controlled photonic elements, and I will be 3 chapters about detectors, about the filters and amplifiers. And you see here a picture on the bottom right side, and this picture is the characteristics picture you will see many times. It shows the specific field effect transistor. This is grating gate. This is not one gate, but many gates. And you see the current flowing through this. and you see the terahertz pulses or terahertz radiation coming in and out. And this is an illustration of a dream that I will be talking in the third part, is to make transfer of energy from current to the terahertz pulses and make terahertz amplifiers. They are still in the range of dreams. So therefore, the lecture is planned to tell you about what exists, detectors and filters, and the third part will be about our dreams and current activity. So this is a kind of lecture and kind of seminar. That idea is to give you the basic notions of the plasmonics, but also to tell you a few words about our current research and encourage you maybe for collaboration with our laboratory or joining us as a collaborator or maybe a member in the future. So some basic formulas, very basic, and there are only two of them in my slides. The rest are simple derivative of this one. First is a well-known formula for plasma frequency of the free electron gas in solids. And in solids, you see the plasma frequency depends on carrier density. Higher carrier density, higher plasma frequency. Depends on the mass of the carriers and on the electric properties of the media. One thing is very obvious from this, that if you want to have a different, if you cannot make a plasmonics with the 3D systems. Why? Because the control of the frequency is very poor. You can change frequency only by changing carrier density. Of course, people can change in 3D density by doping, by changing semiconductors, but this is not the control necessary for electronic devices. You see also on the right-hand side, upper right-hand side, something that is called the dispersion relation, that tells you what is the relation between the frequency and the wavelength, or in other ways, the wavelength is expressed by the k vector, and k vector, you should remember, it's p or 2p divided by the wavelength. So k represents inverse of the wavelength, and this dispersion relation tells you what is the relation between the frequency and wavelength, and tells this frequency that is this relation that is flat tells that the frequency of the plasma waves in the 3D does not depend on the wavelength. You can have it all wavelengths propagation with equal, and they will have the same frequency. And then I come to the limit case that is most important for the seminar, is so-called gated two-dimensional gas. First thing, when you go from 3D to 2D, you get one very important control. In low-dimensional system, and this is something, a message to take home. In low-dimensional system, plasma frequency depends not only on carrier density, that is evident, but depends on the size of the object. And it's not obvious for everybody, but you should know, if you take a sample that is 2 millimeters, 3 millimeters, 4 millimeters, with the same carrier density, they will have a different plasma frequencies. So this is very important message on the basis of lecture. You should think about the two-dimension or one-dimension systems, low-dimensional systems, change frequency with the dimension. And this is expressed here in this formula by the fact that you have a k vector here in the dispersion relation. You see, now the plasma frequency, is equal k, proportional to k, so inversely proportional to wavelength. And why does it mean that this is? Why does it mean that this changes the plasma frequency changes with size? Because the wavelength is defined by dimensions. Why? Because if you put it zeros of the oscillations at the border of the two-dimensional gas, you determine the wavelength. So different wavelengths will have the different frequencies, and these wavelengths are determined by the size. So Of course, you have the control of the plasma frequency by the carrier density. And there is another value here. It's the D is the distance of the gate or the metallic plate that changes the carrier density. And this, if the D is very, very big, you come to the so-called ungated gas with slightly changed dispersion relation. But I don't want to put here this relation, doesn't bring new physics to it. Most important thing is you see here that you have a plasma frequency. All the beauty is this formula. Why? Because you can get a control of the plasma frequency by the size of the object and by the carrier density that you can regulate now by the voltage. And this is something fantastic. I will come back to this many times during my lecture, because this makes plasmonics beautiful, because you get whole control of the plasma frequency. So one very nice analogy, and this is the physics. This is way of talking about physics by Michel Diakonov, but I try to learn as much as possible. He developed so-called sound wave analogy. Why? Because dispersion relation is very similar. Dispersion relation for the sound is that the plasma sound frequency is proportional to the k vector, so inversely proportional to the wavelength. And small letter s here is so-called the s here is the speed of the plasma waves, and the speed of the sound corresponds to speed of the sound waves. And of course, in the formula above, this speed of the plasma waves is here shown under square root. This stuff under square root determines the speed of the plasma waves. So plasma waves are density waves propagating in the charged gas, and they propagate similarly to sound. And this I like very much slide that I taken from Michel Diakonov, that gives you a parameters that you understand that very often physics you can understand as by talking about the orders of magnitude. First of all, look on the picture. That's the vibrating picture on the left side is the picture of the sound waves in the musical instruments. They are sound waves, density waves, and these are like plasma waves. What are the differences? Well, differences are in two differences. In the case of sound, usually sound instruments have dimensions from 0.1 to 1 meter. Then speed of sound waves, many of you should know, it's 30 meters per second. And frequency that you can reach maximal is just the division of the two things, the speed of waves division by L. And if you make the simple division, you will get the frequency that you get for the sound, typical frequency for the sound instruments. You will get 0.3 to 3 kilohertz. So these are the sound waves. You understand the sound waves. What about the plasma in field effect transistors? Two things change. Dimensions. First thing, dimensions of the field effect transistors typically now are 0.1 to 1 micron. If you make a cavity 0.1 to 1 micron, and you know that the plasma wave's typical speed is 10 to 6 meters per second, then you division of these two numbers give you that the range of the frequencies that you can cover with field effect transistors are from 1 terahertz to 10 terahertz. So then one important remark, how is it possible that now you have kilohertz and terahertz? Yeah, you change the size of the object and you change the speed of the waves, but nature of the waves is the same or very similar. But one important thing, you need to get to reach the frequencies micrometer size of the cavities. Therefore, this plasma wave electronics was waiting for so long time. Why? Because you need to be able to make electronic objects. They are smaller than 1 micron. So you need nanotechnology for this. And therefore, even if the idea was known from 50s, already 30 or 40 years old, the real devices could appear only in last decade because the nanotechnology possibility of making the objects smaller than 1 micron of 100 nanometers, 10 nanometers, whatever, it appeared only in the last 1 or 2 decades. So nanotechnology, plasma waves are like sound waves, but it's not enough to make the music instruments of 1 meter long. You need to make a transistor that the field effect transistors that are below 1 micron to get the frequency in the range of terahertz. And this is another message to take home to understand why the plasma technology, plasma electronics can work now and could not really work before. But the plasma in FETs are then better in sound. And you can understand it very well from the fact that the plasma waves are better than sound, because in the case of sound, you cannot modulate, or it's difficult to modulate the air density. But in kinds of plasma waves, you have this magic electrode of gate, and that you can change the potential of the gate, and by changing the potential, you can change the carrier density. So you can not only to reach maximal frequency in terahertz, but you can also tune it from 0, because you can practically make this channel of the transistors empty. You can tune it from 0 to maximal frequency. And simple algebraic transformation of the formula I gave you before gives you the frequency, plasma frequency in field effect transistors that is written here. It is inversely proportional to the length of the transistors and square root of the voltage. And this gives you this beautiful control from 0 to 7 terahertz if you put typical values of 1 volt and effective mass of gallium arsenide or gallium nitride, and you can modulate the frequency by the dimension of the object, and dimension of the object is here. And I repeat, it comes from the fact that frequency depends on K, and K is defined by the length. And what they were dreaming, Michel Shuri, Michael Diakonov, is about just plasma waves propagating in channel. You have here the case when the plasma waves is the case. They can be resonant, they can be standing waves, they can be also overdubbed. All the types of the waves can happen in the plasma of in two-dimensional field effect transistors. So 2 main messages. Plasma waves in nanostructures can reach terahertz frequencies, and the frequency can be tuned by the gate potential. And these are the main things that makes this technology this beautiful and applicable for the real world. I would like to remind you that I promised you to talk about the detectors, then filters and amplifiers. And for detectors, task is very easy because you had a big lecture last week by Alvedas, who was talking about the field effect transistor, plasma wave transistors for detectors, and you get the basic knowledge from this. So it happens that nonlinearity of plasma in the transistor can lead to detection, and I will not go into detail of the mechanism of detection. Keep that nonlinearity of the transistor or plasma system leads to detection. I just wanted to show one result. This is results of the real silicon technology. What you see on the picture is you see it here, gate, drain, and source, 3 electrons of the silicon field effect transistor. And these are the real transistor produced in the laboratory STM Electronics under supervision of Professor Skotnicki. And this transistor had a gate length of around 120 nanometers, so 0.12 microns. So this is submicron is field effect transistor. And what you see here down on the graph, on the horizontal axis, you see the frequency. It's not the terahertz frequency, it's the frequency of modulation of signal. So the signal was modulated here at 77 hertz, but this signal was the carrier frequency was 0.7 terahertz. So 0.7 terahertz signal was detected, and the detected signal with respect to noise has many different orders of magnitude difference. And this many orders, look here, is the logarithmic scale, 10 to minus 7, 10 minus 9. What does it mean? That the signal to noise obtained in this room temperature experiments at terahertz frequencies was extremely good. So good that it was one of the most sensitive terahertz detectors. You maybe remember that the numbers that characterize the detector is so-called noise equivalent power. That means power that is minimum power that is necessary that the signal on the detector overcomes the noise. And this power, the smaller is better, and here is 10 picowatt if your detector operates in the band of the 1 hertz. And this was room temperature big success. It's not so old, it's 20 years old, but this opened the era of the plasma wave transistors and cameras and so on and so forth. And this is our success and success of many groups of Professor Alveda's, German groups, American groups join us. And one of our success was the construction of systems with these detectors. I have not mentioned, but you can maybe guess why these detectors from field effect transistors are so important, because you can produce these field effect transistors by thousands. So you can make matrices, and you make matrices, you can make imaging. And this is what I'm showing you in this slide. You see here on the left-hand side, you have a small picture of the photo from the postal scanner, in which you see the envelopes with the CD disk, and you see the visible image superposed on terahertz image, and terahertz image that terahertz waves goes through the envelope shows you the image of the hidden disk that was not visible earlier. And this is a success of the company of Wojciech, guided by Professor Sipek from Warsaw Technical University, and a team from the Institute of High Pressure Physics, Polish Academy of Science, and the team was guided by Greg Cywiński and myself. And you will see something about this scanner later, because we had some publicity film and so on and so forth. But I would like to mention about another success that was reached in France. You see on the right-hand side the technical director of the enterprise that we created in Montpellier. This enterprise is called Terahertz, and this what he's holding in the hands is a handheld camera, terahertz camera, where is the source and detectors, and he's checking the quality of the glue on the windshield of the Renault car. So this was really the industrial order to check quality of some plastic or glass. You need to construct the handheld cameras, and it was constructed in France, and it was based on these detectors. And just to illustrate part of detectors by something, I show you the publicity film of the postal scanner. It exists at Cesamat. You can come and see it. It's historical object. It's 20 years old, but still working, operating. You see here electronics with many transistors detecting the image. Hidden objects in the envelope can be found. It has a 1 millimeter resolution. You can find biological species and powders. We claim it's easy to use. And we were making this publicity to put this scanner on the market. And this is a success, I told you, of Unipress and Ortech. These two institutions were working together with the money of the Mazovia department. So this was first terahertz postal scanner, but we never managed, and this is a a kind of the lessons that you should learn. We have never managed to put it on the market. Why? It was too expensive. It used the United States produced sources with that costed 20,000-30,000 euros. Complicated optics, needed space. It was too big and too expensive. So, but it was a beginning of good story with detectors, because now at Centera Labs we are working on silicon technology to have a silicon sources and detectors to be used to lower size and costs, and we hope that Centera will be able to produce a new version of the scanners that have the size and costs acceptable for the market, and will be trying to make the technology transfer for the quality control or the security during the next years of Centera activity. So this remark finish my part about detectors. I will not talk much about the detectors now, and we come back to our plan. I promised you to talk about detectors, filters, and amplifiers. So we come to filters. Can we make a filters? Or it's filters with plasmonics, and now it comes the hero, the grating gates. But the real heroes of the story, the main people responsible for the results that I will be talking about, Pavlo Sai, Maxim Dub, and Vadim Korotyev. They are from Centera Lab at Cesamat, from Institute of High Pressure Physics, Polyacademy of Science, and also from Lashkarev Institute of Semiconductor Physics in Ukraine. They are working now with us. They continue working, and they work with us on the basis of different projects. One of important projects that I would like to mention is ERC Advanced project 2023-28 that has to, as a goal to make on-chip plasmonic amplifiers of terahertz radiation. But the first step on making these amplifiers in the ERC project and in Centera project too was to make the things that can have a nice plasmon resonances, and then try to use these resonances for amplification. So we stay with filters, and to make the filters, we first think we have a challenge. This is the first thing, what kind of the material to choose to make these filters. We have chosen gallium nitride, not only because at Unipress gallium nitride technology is accessible, but also this is material with high carrier density, with relatively high carrier mobility. High optical phonon energy has importance for amplifiers, but it's also important. But this also material that you can have a big size wafers, so the size is important. You can make a millimeter size samples, and this is a crucial thing. You can think about the graphene, for example, that has high carrier mobility and high carrier density too. But to have both of them, high carrier density and mobility, you can get it only on flakes, 20 micrometer sample, and these are not practical. So you need a system that you can epitaxy to make real filters. And this is challenge. This is a slide from Pavlo Sai presentation, shows you what was produced in the frame of Centera project or ERC project. We produced the systems, and you have a gallium nitride substrate. Then you have aluminum gallium nitride barrier, but between them you have this red line. This is a two-dimensional electron gas. So this is created two-dimensional system. For the moment, when you make a wafer, it's kind of infinite. Now I told you to make a terahertz plasma, you need to make the objects of the size of micrometers, right? So what was done in technological room was done the grating, and what you see like here is the total vision of the object that will be. I will try to show you that this is a really good filter. It's the object that has you here. You have a scale here 300 micrometers, so the object has of millimeter size. But object is of millimeter size, but I told you the cavity of plasmons should be micrometer size. So you need the thousands of the cavities on this object. And what is thousands? There's thousands of the grating fingers. And you see them here on the picture. See the picture, here fingers, grating fingers with 0.9 microns, and the period of this grating was 1.5 micron. This is one of the example, typical dimensions. These dimensions goes to 0.5, even sometimes 0.3 microns. But you see immediately the challenge that we have to face in the terahertz manipulation. The terahertz beam, terahertz wavelength is of the millimeter size. The wavelength in air of the terahertz, 1 terahertz is 300 microns, so 0.3 millimeters. And plasmonic cavities should be micron size. So you have to produce the object that efficiently interacts with incoming terahertz beam that is drawn here. You need to create the object of millimeter size, but with thousands of the plasmonic cavities. And this is a very important technological challenge that was overcome not very long time ago in the frame of our projects. So one of the sample that is presented here on the picture, you see here 2 millimeters by 2 millimeters, you have a source drain, and you have this grating gates here. Now that has a 2 millimeter by 2 millimeter and thousands of the fingers on it. So thousands plasmonic cavities, but you want to have a control on them. So what on this plasmons that oscillates in these cavities. So you have no right to make one error. All the fingers should be not leaky. You should that means you need make 1,000 similar non-leaky transistors. Leaky transistors means that your gate is not working as a gate, but if you apply the potential to the gate, the carriers comes from metal from the gate to the channel, and this perturbs all the plasmonic activity. And this was achieved, and we could study them in the Fourier transform spectrometry, and these are the results obtained by the group. The experiments guided by Maxim Dub, by Pablo Sai and Yuri Woniak. Also Maciek Sakowicz was participating in first steps of Fourier transform spectrometry here. So these guys obtained the spectra that are shown on the left-hand side. And I would like to spend a few seconds on the spectra. What is this spectra? You will see here the dots, that's the experiments, and then you see the lines, that is a theory. So of course, everybody likes that theory agrees with experiment. It agrees relatively well. But most important information from the graph, I would like you to mention two things. First, that you see here the lines, and these lines are plasmonic absorption, because this is a transmission. Every minima here means absorption. So there is a plasmonic absorption at this frequency, for example, on the first line. And what is the parameter? Maybe first, what is the parameter on the line? Parameters on this is the gate voltage. In other words, this is the carrier density under the grating. So here you have a high carrier density under the gratings, and here have no carriers at all. And then something happens even if you have no carriers. I will explain you a little bit later. But what you see when you have a carriers under grating gates, you see first plasmonic harmonic, second plasmonic harmonic. When you go to voltage, to lower voltage, the carrier density changes a little bit, is smaller, and this frequency, first harmonics, goes smaller, and second also goes smaller. When you make still smaller carrier density, harmonics go smaller, second smaller, and your experiment window appears the trace of the third harmonics. And when you go down and you see better and better third harmonics, when you see here in the low carrier density, you see the first, second, third, and even fourth, slightly marked in the theory, a little bit less seen in the experiment, but this harmonics exists anyway. And then happens something strange. There are no carriers under the gate, and you see some plasmonic lines that now, with the more and more negative voltage applied to the gate, it moves in the opposite direction. It moves to the right side to higher. So you adjust the shift to the red when you have the carriers under the gate, and you shift to the blue when you have no carriers under the gate. And this is illustrated in this chart. So you see here plotted as a gate voltage, or you can understand as a carrier density under them, the resonances that we observed. So this is first harmonic, second harmonic, third harmonic, and then this strong line once you have no carriers under the gate. But be aware, there are no carriers under the gate, but between the gates there is ungated gas, and this is the plasmons related with ungated gates, but with ungated stuff. This is what is explained on this figure once more. Look what's going on. You have this plasmonic fingers, metal fingers. So this is gate fingers here. So with them, you create the cavities with carriers. And the carrier profile, so you see here the potential, battery, metal here that makes more or less electrons. And the carrier density profile is shown here. You see here, this is the distance in the sample. You go through the grating gates, and you see higher carrier density. N0 is between the fingers because there is no gate. So it's always, and under the gate, you can have a carrier density that is changed by the potential. And then again, you come to N0 between the fingers. And then again, you have some carrier density between that you can modulate. And of course, you can come to the case when you completely close the channel. This is the case shown on the lowest picture. Then you have a N0, N0, N0 in ungated parts, but in gated parts you have a 0. And what we discovered that these two states shows completely different spectra. You see here the experimental curve up there that I repeat from the previous slide, and theoretical slide here showing that effectively you can see, you can have these plasma resonances. They have different nature. Why? Because on the right side, when the carrier density is everywhere here, and all these cavities are connected with higher carrier density, lower carrier density, you have something that is called delocalized state. This whole system reacts as a crystal. There are no separate cavities, but this whole system reacts as a crystal, but crystals in delocalized phase, we call it, because the plasmons are delocalized between the grating parts and ungated, gated parts and ungated parts. Now, when you go to this situation that you have no carriers under the gates, there are no plasma oscillations under the gates, there are no carriers. So the oscillations take place in ungated regions. And this is, therefore, these oscillations are localized in ungated region. And therefore, we have a kind of the phase transition because delocalized plasmonic crystal and localized plasmonic crystal. There is a strange thing happens here. I'm not going to tell about this, that normally you change the gate voltage. It should not influence the part between the metal, but influence anyway, because you make something that is called, you make by applying more and more negative voltage, you make something like shrinking the dimension of the channel, and in narrower channel gives a higher frequency, and this is the effect that you see here, and this is the effect that somehow unexpected, but now we understand it. Where does it come? Where does it come from? So this is now you see you can make beautiful filters. You can use the filters with 3 lines or with 1 line. and you can tune the frequency of the filters by the gate voltage between the 0.5 and 3 terahertz. You can change the range of the frequency by making this cavities higher or smaller, and you have a perfect filters, and we are currently working how to use these filters, multi-line filters, to make a electrically controlled spectroscopy. Excuse me. Because you imagine that having such filters, you can do a beautiful spectroscopy. You do not need any moving elements, any gratings, any beam splitters, nothing. You just put your filters in front of your unknown source. You can analyze it by checking what kind of the, at given voltage, what is the signal. You change the voltage, you know that your frequency of filter changes, and then you can deconvolute this, signal as a function, measured as a voltage, a function of a voltage, and find the spectrum of unknown terahertz source. So these filters can be used and will be explored and will be put on the potential commercial applications in the works of Centera. And this is one of our success that we are very, very proud of. This is the last year publications in Physical Review X that we consider as one of the most serious physical review. This comes from the Physical Review, American Physical Society journal, very serious, existing since years, and very seminal, only seminal papers, important papers are allowed to be published there, and we are really happy that we managed to have these publications showing for the first time electrical tuning of terahertz plasmonic crystal phases and switching between the localized and delocalized phases, but showing first that plasmonic crystals, that GaN plasmonic field effect transistor behave always as plasmonic crystals, not as a sum of single plasmonic cavities. This is first conclusion out of a work. And second, that the grating-gated GaN plasmonic FETs may serve as electrically tunable terahertz filters. So we come now then to the second part, end of the second part of the talk. It's 1 hour. I still have for 15 minutes, and I suggest we continue now 15 minutes more about amplifiers, because it's kind of it will be relatively light part of seminar. So what you see on the picture here is just the scheme of the first system that have shown amplification. What does it mean, amplification? Amplification means that you put the terahertz pulse on systems, and this system is, in our case, plasmonic system, and what is reflected out of the system, or it can go through the system and then be reflected from the back mirror, gives you more intensity than intensity of the radiation that was than incoming radiation. And how is it possible? Where do you take energy from? You want to take energy from the current flowing through the structure. You want to transfer energy from the current to plasmons, and from plasmons to the radiation. This is the idea of the plasmonic amplifiers. So you see here a very trivial picture that it is forgotten to show in any serious terahertz presentations. But what I'm going to show you now 5 slides that European Research Commission ERC panel council wants you to show presenting your project. I was obliged to present the project, so I will make, and you have to do it in 5 minutes. So next 5 minutes, I will show you presentation that allowed us to get this ERC project. Therefore, you see for the commission and the experts that do not know what is terahertz, you see this axis with the showing this terahertz gap and telling that it has a high application potential for quality control, safety, telecommunication, but there are no cost-effective compact solid-state amplifiers and sources. And then you see on the right-hand side, down there, the free electron laser. That is the free electron laser that gets the terahertz radiation by modulation the movement of electrons, beam of electrons. And of course, what we propose is TeraPlasm solid state physics project, in which we would like to make a kind of the analogy of this free electron laser by using semiconductor grating-gate transistor. And you see already that these magnets in the free electron lasers have at least similar geometry to the grating gates. So what we promised, but first, of course, you have to present, why doesn't it, okay. You have to present your carriera and main ideas. This slide you have seen partially. So carriera about the plasma waves and all my way, and that plasma wave terahertz detectors were success. You have heard about it. So it's easy. I will go further, and with creation of Terakalis and Ortech, you have heard about it. And you show to commission, okay, we have a kind of the success in commercialization. And now we dream about plasma waves to make something more. And everything was based, and the main idea was based on a breakthrough discovery, breakthrough results that I can talk now just for 1 minute. That you take this grating gate transistors, you put the current, and you see that you get more intensity when reflecting the radiation from this structure. And this is our PRX paper 2020, it was basis. And we are showing that this blue valley, that is plasmonic absorption, when you put the current to the structure, transfers to this red hill, and this red hill is the terahertz amplification. I will talk about it more in details later, but I just keep here the narration a little bit from this ERC presentation. And of course, you have to present what are your challenges. So challenges in the project was find physics behind this PRX results, and then explore new phenomena. So this physics was very strange because there was plasmonic absorption, that silence gap, no absorption at all, and then amplification appeared. And what we proposed, challenge and approach, we proposed to use use mercury telluride. Why? Because these results were obtained on graphene, and graphene is given by God. You cannot change anything, but if you take the quantum well of mercury telluride, then you can make a quantum well a little bit wider or narrower, and you can get the graphene-like band structure, or you can make an open gap structure like a normal semiconductor. So we proposed use the mercury telluride quantum wells. And second promise is we promised to compare plasmonic crystals and to tell whether they, whether they work as a sum of individual oscillators or they work as a crystals. And you see that the first part of the answers we already gave, it's already given. You have seen this in the case of the filters, but this is what we proposed in 2021 for the ERC. And then we propose also to study some other plasmonic phenomena that I will not talking much. When you have two planes of plasmons, and they exert something kind of friction, you can have a turbulence, and this turbulence also can make a terahertz radiation. But this is a subject that I'm not going to talk more in detail still, and the first theoretical considerations. But there is a nice meteorological analogy of the streams of the hot and cold air streams that leads to this fantastic turbulence of the clouds, and this phenomenon that we hope to explore was proposed to ERC as an additional phenomenon to create terahertz. And when we propose, you have to show that you can implement your project, and implementation is because we had this nanotechnology lab with all technologies necessary, and lab was fully equipped. But you can make a nano device processing, and you see here this grating gates. And then we had at the moment the first plasmonic pictures of plasmonic crystals, and then it was somehow successful, and European Research Council wanted to believe the TeraPlasm project will bring the big discoveries in science that will explain three things: influence of relativistic dispersion on plasma properties, physics of plasmonic crystals versus ensemble of individual resonators, and explain 30 years old problem of terahertz amplification by plasma in solids. So to answer the question, can we make the analog of free electron lasers using small transistors? And of course, you have to make publicity about society application for non-destructive tests, security control, or high data rate wireless communication. Maybe I will tell 2 words about this picture that not many of you are considering this, but this is a driving force of terahertz technology. You see here a kind of the system. I will show him bigger in the next slide. That is a kind of the configuration of the amplifier that should be used to telecommunication. So telecommunication, we have to send signals wireless between different sites, but the signals get weakened in the air. You have to amplify it. And what we propose in the project was amplifier. When you have a terahertz source, you have a mirror covered by this plasmonic amplifier. And then by putting from battery current to this plasmonic amplifier, you get a reflection higher than intensity higher than comes, so you had amplification. You can make a 2 mirrors or series of mirrors to get amplification. This is what we proposed. But let's come back to the physics, what happened in this experiments. I went through this very rapidly just to show you what you have to make as an exercise when you want to fight for ERC project. You have to, I repeat, to tell a story of your life or project and tell that society will be happy with it. Really difficult task. You have to learn it if you want to fight for ERC project, but it's worth. So what we observed, you see here the frequency on the horizontal axis and the absorption on the vertical axis. And you see plasmonic lines here on the left-hand side picture. You see the blue and dark and black, blue, and green lines that move to the left. What is this? This is plasmon lines that move to the left with applied current. So current was modifying the plasmonic structure. This is what we see. And what you see here on this graph that shows only frequency. Frequency was going down. You see frequency going down. At certain voltage, we get something completely plasmonic silent crystal. And then after some gaps, you increase voltage. And what you see, oh, I have again my plasmonics, but it's this positive absorption starts to be negative. And negative absorption means in your experiment amplification. That means that you get a more light reflected from the sample than incoming line. And this was this breakthrough experiment that allowed us to change to claim that we maybe will make humanity happy with terahertz plasmonic amplifiers. However, the challenges were following. This was obtained of the small graphene flakes, samples of 20 microns. So what to do next? This is repetition of this Blue Valley and Red Hill again. Absorption that comes to amplification and reference to our paper, but also reminder that this was obtained on 20 micrometer flakes. So one of the challenges was to go to the real big samples, and your flakes is much smaller than the 1 millimeter size of the beam. How you can do? You have to get scaled graphene or gallium nitride technology, and that's important that you have to scale it and keep this amplification. And why gallium nitride technology? I come back to this same slide, because you have a high carrier density, high carrier mobility, and here comes high optical phonon energy. And this high optical phonon energy is important because if you want to take energy from the current, you should speed up electrons to high drift velocities, high energies. And one of the limitations in many crystals is the fact that when you speed them very fast, then start to shake the lattice. And how they shake the lattice, you have emission of optical phonon energy. You do not transfer energy to plasmons, but you transfer energy to phonons. So it's important to have high phonon energy. Gallium nitride is a good material because of the high carrier density, high phonon energy, and high carrier mobility. So we can work on millimeter square samples. You could see this on the plasmonic crystal filters part of my exposé. So next step, what we are working on is to understand the role of the current. And we do not have the answer. Will we manage to make the real good size terahertz amplifiers or not? We know now for the moment that we can make nice gallium nitride plasmonic crystals. We'll be doing also mercury telluride plasmonic crystals and graphene plasmonic crystals, pushing the current through it and trying to get amplification. And this ends the story. What I wanted to tell you about detectors, filters, and amplifiers. Detectors is a success story. Filters is a good progress because we have already filters. We have to put it in application. Amplifiers is still not known country, not known part of the physics. We hope to be successful, but still is a high risk, but also high gain project. And final remark, as I told you, historically, plasmonic stuff is known for more than 50 years. 2D plasmonics were developed by Chaplik, then by Allen in Bell Labs, and then by Diakonov Shur in 90s, so more than 30 years ago. And the progress is relatively slow. And why? And why we think we can make it now in Poland? Because we can join the forces acting in the same place and time. We have a materials technology, GaN-Algan and graphene, and also mercury telluride since few days. Greg brought nice samples from Rzeszów, so we have mercury telluride also. We have nanometer technology processing that can go up to millimeter scale. And it's really challenging. People that know what that means, nanometer technology, and how to make it big up to millimeter scale. They know that's really a big challenge. And we have a fully equipped spectrometry lab and team that helps us to understand what we are doing. And this is all summarized here. And we hope that now, after this 50 years of research, we can bring people to get successful detectors, amplifier, filters, and amplifiers. And this will be done in Center CESAMAT Project Center 2. So at this moment, I think I am ready to take any questions. Hello?
Yes, hello. There? Thank you for a great lecture.
I was afraid for a minute that I was talking to the...
No, fortunately, we could hear your talk.
Because I hidden your faces to have a picture on there. And then silence scared me that I was disconnected maybe for 1 hour.
No, it's very fine. We needed the moment to unmute ourselves, Professor. Okay, we actually have one question from an anonymous attendee who did not want to publish their name. So let me read that question to you. Can two-dimensional plasma waves propagate in infinite plasma medium just like water waves can propagate on the surface of infinite water tank? I'm not talking about infinite wavelength disturbance, for which frequency would be 0 according to dispersion relation.
Yeah, they can propagate, of course. They can propagate in infinite, like on the waterways. There is, by the way, very nice also analysis developed by Diakonov that shallow water has the same equations that plasma waves, and the same equations have the same solutions. Only the letters change. So the sound waves and shallow water waves are very similar to the plasma waves. And by the way, this gated and ungated gases in the grating gates are very often simulated or as a deep water and shallow water cavities with different frequencies of the different dispersion relation of the waves.
Okay, thank you. I think also Tim Zauba had a question, but is a bit shy to put it into the Q&A section, so we'll wait for Tim for a little bit. In the meantime, maybe I'd like to ask a question as well. So all of the plasmonic part that you've mentioned, most of it has to do with propagating plasmons. What about localized surface plasmons? Do they have their place in terahertz applications? And probably due to sizes, it's more limited, but could you comment a little bit on that?
Depends what you call propagating and localized. To get a given frequency of oscillations, you have to localize them. This frequency of the oscillations is defined by the size of the localization. More you localize, higher frequency it is. This is therefore you have to localize to 1 micron to get terahertz frequency with typical other parameters. So they are all localized if you want to have to define frequency. And then you change frequency by changing density by the gate, right? So these are all localized plasmons. Similar to metal stuff, also if they are localized, maybe you can, if you localize, here we localize typically to 109 nanometers, and then you have a few terahertz maximum frequency, and you tune it by the gate voltage. So this is very similar phenomena. They are also localized.
Yeah, can I ask a question that is closely related? Because your gate has this shape that looks like plasmonic cavities formed by Professor Mona Jarrahi that is used to enhance the absorption at near infrared or near visible wavelengths. So does it mean that your FET transistors also have some response at near infrared or visible wavelengths? Because you can excite optical plasmons that exist on the surface of your material. Would visible or near infrared light have an influence on the behavior of your system?
That's a very interesting remark. We never thought about it. This reminds a little bit Jarrahi stuff. I fully agree. This fingers in Jarrahi stuff, these are the fingers of photoconductive antennas.
That's correct.
So this is I don't know. I do not know how to merge these things, because in photoconductive antenna, between the fingers, you want to have a highly isolating gallium arsenide that when you shine the light, then you create the carriers that are accelerated by the fingers, and these carriers produce terahertz stuff. Here we have some samples with the gratings that can be polarized in different directions and have currents flowing, but it will be not fast currents producing the terahertz pulses. They will be going to gigahertz or whatever, because you have capacitances. So this is completely different phenomena, but you are absolutely right. The geometry is similar, and maybe it's worth to think about kind of mixing devices. If you take a piece of gallium arsenide, for example, you can think about, this comes to me just spontaneously to head, but all the gallium arsenide devices are made of semi-insulating substrate. If you take a semi-insulating substrate that you can make on one side, probably this Jarrahi generator, and on the other side of the crystal, you make two-dimensional electron gas with high mobility, and you make another gratings that will be plasmonic detector or filter or modulator of this radiation. I don't know, whatever. This can be a funny devices that follows your great remark that these geometries are similar, and why not to think about this fantastic devices. I don't know what kind of advantages can take, but we have to discuss with Jarrahi maybe, or you have enough competences to it. I'm looking forward for discussion. What can be used this for?
Yeah, the straightforward question is what happens with your terahertz field electric transistors when they are illuminated by the terahertz, let's say near-infrared wavelengths, but probably you can only speculate.
Depends on material, because if the plasma frequencies are in terahertz range, so they are infrared, they are transparent. If the substrate is transparent, so surely if this gallium nitride, so this infrared stuff goes through, although one can expect also some grating effects, some diffraction effects. So question is whether we can couple this infrared light to this plasmons and how strong coupling is. Probably yes, especially if you create very non-uniform profile of electric field, and you can create it by taking electrons out of the gating parts. So you have regions of very strong electric field in it, and in this strong electric field, you can maybe count of some nonlinear phenomena. This is what comes to my mind but I am positive to try. Positive to try because both your ideas shows that the people from different worlds should meet together to create some fantastic ideas. Some of them are maybe genius, and some of them is just fun to check. So I'm really positive we have to check it. So we'll be illuminated, but we need you or your people in our laboratory to understand what we are doing with near infrared, because we are limited in the spectral range.
Okay, thank you.
Of our knowledge. Lasers we have. You have seen it, so feel free to choose laser, and then we'll do your experiment. It's your experiment. We're waiting for you.
Yeah, thanks.
Beautiful. Okay, I see we have another question. In that case, probably from the same author as that asked the first question about the water. In that case, what is the plasma frequency formula for the two-dimensional case? In three-dimensional case, this is frequency, which determines what frequency will be reflected or propagated through plasma.
Now, in three-dimensional case, the plasma frequency is not defined by the dimension of the object. No way. All the wavelengths have the same frequency. This means the flat dispersion relation in 3D. In 2D, in 2D, when the bigger object is, the dimension of the waves that can propagate in it, I mean the bigger wavelength is, right? Because if the wavelength is defined by the borders of the sample, of course you can have harmonics. Then you have a shorter wavelength, but the longest wavelength is determined by the dimension of the object. So and you keep always the same formula. The formula tells you what is the relation between your wavelength and frequency, and we tell if you increase the dimension of the object, that means your wavelength is bigger and bigger, your K vector is smaller and smaller, and this dispersion relation tells you energy of the plasma excitation will go to zero. Very long wavelength. This dispersion relation, omega is proportional to K, means that if K is going to zero, that omega is also going to zero. So if you make it object bigger and bigger and bigger, you come from terahertz to gigahertz, from gigahertz to megahertz, kilohertz, and then to zero. So this is what tells you this dispersion relation and the behavior of two-dimensional electron gas on the surface.
Okay, the further question is, I am asking about 2D plasma frequency for infinite medium case.
In the infinite medium case, that infinite medium case, if you have infinite medium, you have a zero plasma frequency. If you I mean, yeah, you can also have propagation of the harmonics, but the harmonics are low frequency. So it will be the frequency will go to zero anyway.
Okay. So
you take big wafer of two-dimensional electron gas, you check for plasma with Fourier transform spectrometer. It will not show you any plasma edge. This is what answer of experimentalist.
Okay,
you usually look for the plasma in 3D light. What do? You put this 3D plasma, like highly doped gallium nitride, you put to your spectrometer, and you look for the reflection. Below plasma edge, most of the radiation is reflected. So the plasma edge will be plasma frequency for the 3D determines very often people use it to determine the carrier density, right? So where is the plasma edge for 2D or plasma absorption for 2D? If the 2D is infinite size, it's 0. There is no plasma reflection, the plasma edge.
Yeah, so the follow-up answer is that you still have water waves on the ocean.
Yes, you have the waves on the ocean, yes. Kind of philosophical question. I have to think it over. But I was most of my time focalized on the small transistors, never thinking to make the dimensions to ocean dimensions. You can have this plasma waves on the oceans. They are plasma waves on deep water. The wavelengths are as they are.
I think you can continue this discussion via email.
Understand, yeah.
Yeah, so if this person is not afraid to show their name, we invite to write an email.
I know who is asking this, but I can have him in my lab, this guys.
Okay, so the person thanks you for answering, and he will move to or she or they to email. Okay, so with this amazing Q&A session, I'd like to thank everyone, and especially Professor Knap for today's lecture. Also, next week, we'll have Agnieszka Siemion, who's also present here, the co-chair of the whole lecture series, who will tell us about terahertz optics and optical elements. Okay, so thank you for joining in today, and see you all next week. Thank you very much.
Thank you. Thank you.
Thank you.
Bye-bye.
So, goodbye. Thank you very much. And thank you for remarks for Łukasz.
Yeah.
And we have a plan for experiments, right?
Yes. Okay, thank you. See you later. Bye.